In this video, we're going to give an introduction to the method of undetermined coefficients for solving non-homogeneous second-order ODEs. So we're looking at differential equations that have this form: ay double prime plus by prime plus cy equals g of t, where a, b, and c are reals, a is non-zero, and that's what makes this a second-order ODE. And g of t is now a non-zero function, and that's what makes this non-homogeneous. So the question that we want to first try to answer is, what does a general solution to this look like? So to answer this, let's begin by letting y sub p be a particular solution. So that means y sub p, we're going to let that be one solution to our ODE. And let's let y sub a be another solution. All right. So the fact that y sub p, we're saying that that's a particular solution, that's one solution, means that when we plug it into this differential equation, it satisfies it. So that means that a times y sub p double prime plus b times y sub p prime plus c times y sub p, that should be equal to g of t. But for the same reason, when we plug in y sub a, we said that was some other solution. We should get a times y sub a prime plus b times y sub a prime plus c times y sub a. Well, that should also be equal to g of t, because we're supposing that that is another solution. So now looking at these two equations that we have, they look really similar. So because they're so similar, what I'm going to do is I'm going to subtract them, because the right-hand side will become really nice. It'll just become 0. And even the left-hand side will be nice, because I'm going to be able to factor out an a out of the first two terms and be left with yp double prime minus ya double prime. Then I'll have a plus b times yp prime minus ya prime. And then I'll have a plus c times yp minus ya. That's what we have on the left. On the right, g of t minus g of t, that's just 0. Okay, so the fact that now we have this equation where the right-hand side is 0 means that this is now homogeneous. And moreover, this function that's sort of being plugged in here is going to be a solution to the corresponding homogeneous system. So thus, this means that the function yp minus ya, this is sort of what got plugged in, into here, but where the right-hand side is 0, that function is a solution to the homogeneous ODE. All right, so let's call this thing y sub h. Y sub h to represent the fact that it is a solution to the homogeneous ODE. All right, so next, what I want to do is I want to isolate y of a. Because at this point, we know that y sub p minus y sub a equals y sub h. If we isolate y sub a, this other solution, it's going to be equal to y sub p plus y sub h. All right, so what's the takeaway from this? So the conclusion now is the general solution to our non-homogeneous differential equation will look like what y sub a does. Y sub a was some arbitrary solution. So the general solution has the form that y sub a does. It'll look like, I'm just going to call it y to make it general. Y is going to be equal to y sub p plus y sub h, where y sub p, this is a particular solution to the non-homogeneous equation, and y sub h, this is a general solution to the homogeneous equation. All right, so let's go ahead and box this. So one important thing that I want to point out about this is, notice how closely this parallels linear algebra when we talked about solving a non-homogeneous matrix equation, and how the form of a matrix equation also looked like this, where we had a particular solution being added to the general homogeneous solution. All right, so now let's talk about the strategy to solve a non-homogeneous ODE. So there are 3 key steps to solving a non-homogeneous ODE. The first 2 all of them we sort of kind of briefly hinted at. The first 2 involve first solving the homogeneous equation, so where the right-hand side equals 0. So to do that, we use the characteristic equation, or sometimes we call this the auxiliary equation. So we use the auxiliary equation, which would be AR squared plus BR plus C equals 0. And then we use our methods from section 4.2 and 4.3, where we talked about how to solve homogeneous second-order ODEs like this. So we use those methods. So after we solve that homogeneous equation, then step 2 is we find y sub p, a particular solution to the non-homogeneous equation. So that means we just have to find one solution to our non-homogeneous equation. All right, so the idea, okay, I don't want to get too carried away. So the idea is we are going to try to guess a solution based on what g of t is, so what we have on the right-hand side of our differential equation, and y sub h, what our solution to the homogeneous equation looks like. And there are 2 ways that we can do this. So the first method is called undetermined coefficients. The method of undetermined coefficients. And this method involves more guesswork, but the guesswork is systematic, as we'll see. And there's another method called the variation of parameters. The variation of parameters. Which is the topic of section 4.6. And variation of parameters in general can be a little bit more cumbersome, but it doesn't involve the level of guesswork that undetermined coefficients does. All right, so let's talk about undetermined coefficients and how it works. So undetermined coefficients is helpful if the right-hand side, g of t, has a very specific form. So either if it's an exponential function, so something of the form a times e to the kt, where a and k are just real numbers, or if it's a combination of trig functions, specifically sine functions and cosine functions, so something of this form, and either the a or the b are allowed to be 0. So we could just have one of these trig functions, like maybe just the cosine and not the sine, or vice versa. Or if we have an nth degree polynomial. Okay, so for functions of these 3 forms, and also for products of functions of these forms, or sums or differences of functions of these forms, the method of undetermined coefficients is really helpful. For anything else, so things like tangent of t on the right-hand side, or 1 over t, or ln of t, things that are not these 3 categories, undetermined coefficients is not going to be helpful. So for each of these cases, I want to write down what my guess will look like. So when we have an exponential function like this, yp, my particular solution, the guess that I'm going to make will be capital A times e to the kt. So our goal here, so a is going to be some unknown real number, is to find a, to find that coefficient. That's why it's called the method of undetermined coefficients, because we don't know what this coefficient is, and we're going to try to guess what it is. All right, so when we're in this trig function category with cosines and sines, then what we're going to guess for y sub p is a combination of cosine and sine. So a times cosine of beta t plus b times sine of beta t. And now there's two coefficients that we don't know. So we'd be trying to find a and b. And then if we have an nth degree polynomial, then our guess also needs to be an nth degree polynomial. So I'll write that as a sub n times t to the n, and then I keep going smaller and smaller until I get to a sub 1 times t plus a naught, where a naught is my constant term. And in this situation, we'd be trying to find these coefficients, so a naught, a1, dot, 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 up until an. So let me also just mention, these coefficients are real numbers. So here a was real, here a and b were real, and here a naught up until an, they're all real. So we're trying to determine these unknown coefficients. In this last row, where the form of the function g of t is anything else, so not exponential, not combinations of cosine and sine, not an nth degree polynomial, here we use variation of parameters. Variation of parameters. So the method of undetermined coefficients won't work. All right. So the main reason, kind of in a nutshell, why undetermined coefficients will apply for these three categories right here is because exponential functions, their derivatives look really similar to the original function. Just maybe an extra constant will pop out, but they look really similar. The same thing is true with cosines and sines. Their derivatives are just other cosines and sines. And with nth degree polynomials, when you take their derivatives, you still get polynomials. But the degree is smaller, but it's still a polynomial. But when you get to other types of functions, like other trig functions or things like ln, and you take their derivatives look a lot more different. So undetermined coefficients will let us handle the case where the right-hand side is nice like this. All right, so after we formulate our guess, we want to plug yp into our differential equation to find what those coefficients are. And after we do, then we want to write our general solution. So our general solution will be yp, our particular solution, plus y sub h, which is the general homogeneous solution. All right, so now let's do some examples. So with these examples, I'm going to start off with some simple examples. And in the next video, I'll start to do more challenging ones. All right, so let's solve this differential equation. So I have y double prime plus 2y prime plus y equals 32 e to the 3t. So the function that we have on the right-hand side here, this is g of t. So our first step is we need to solve the homogeneous equation. So solve y double prime plus 2y prime plus y equals 0. So to do this, we look at the characteristic equation. So the characteristic equation, or the auxiliary equation, would be r squared plus 2r plus 1 equals 0. And we could factor this. This is r plus 1 squared equals 0. And now we could write down what r is. And r is negative 1. Okay, so we have a root, and it's repeated. So negative 1 has algebraic multiplicity 2. All right, so now we're ready to write down what our homogeneous solution is. So y sub h would be c1 e to the negative t. So I take the r, and it's in the exponent as the coefficient of t, plus When I have a repeated root, now I have c2 times t e to the negative t. So multiplying by t is how we created another linearly independent solution, in this case where we had a repeated root to our characteristic equation. So we know what the homogeneous solution is. Now we're on to step 2, which is we need to find a particular solution to the non-homogeneous equation. So we need to find yp using a guess. So find yp using a guess. So we have to look at what g of t looks like, what form it has. So it's 32 e to the 3t. So this is an exponential function. So thinking about what our table said, it says if we have an exponential function like this, to guess that yp is going to be, so we'll have some coefficient in the front, and then the same type of exponential function. So e to the 3t. So I don't change what the power is here. All right. So what we're going to have to do is we're going to have to take this guess and plug it in to this differential equation. So we need to take the derivative and the second derivative of it. So we can go ahead and plug it. So the derivative of yp prime would be 3a e to the 3t. And now let's take the second derivative. The second derivative of yp would be 9a times e to the 3t. All right, so now let's go ahead and plug in. Plugging into the differential equation, so the second derivative was 9a e to the 3t. So we'll have that plus 2 times the first derivative, which was 3a e to the 3t. And then plus the original function, and the original function was a e to the 3t. All right, and this equals the right-hand side, which is 32 e to the 3t. So combining like terms on the left-hand side, we'll get that this is 16a e to the 3t. And that equals the 32 e to the 3t that we have on the other side. So at this point, it's easy to see that a has to be equal to 2 to make this 16a becomes 32. All right, so we are ready to write down a particular solution now. So y sub p, a particular solution. So we write 2 as the coefficient of our guess. So it would be 2 e to the 3t. That is our particular solution. This is one particular solution. All right, so we are ready for the last step now, which is we'll just form the general solution. So the general solution will look like y equals y sub p plus y sub h. So the particular solution added to the homogeneous general solution. So y is going to be, so the particular solution we had right here, it was 2 times e to the 3t. The homogeneous solution we did earlier, and that was c1 times e to the negative t plus c2 times t e to the negative t. And that is our general solution to our non-homogeneous equation. That's how we do it using this method of undetermined coefficients. Alrighty, so let's do another example. Now let's suppose that we want to solve this differential equation. So we got the exact same left-hand side, but the right-hand side is different now. It's t. I have a different type of function. I have a polynomial instead of an exponential function like we had in the last example. So our first step would be, just like we did in the last example, to solve the homogeneous equation. And we did that already, so I've just gone ahead and written down that solution. So the next step is now we need to find a particular solution to the non-homogeneous equation. So we need to find y sub p. So to do that, we need to look at what g of t is. G of t is what's on the right-hand side of the differential equation, and that's t. And based off of that, now let's form a guess. So let's form a guess. So our guess here is going to be y of p. So the fact that this is an nth degree polynomial, in this case a first degree polynomial, means that my guess will also be a first degree polynomial, but just the most general form. So I'm going to write it as at plus b. So it's sort of the most general form that a first degree polynomial could have. And now I'm going to have to plug this in to our differential equation. So let's take some derivatives. So the first derivative of this would just be a, and the second derivative of this would be 0, because the derivative of a constant is 0. All right, so now let's plug in. So let's plug these values into, so we got to plug yp in. So yp double prime plus 2 times yp prime plus yp, that needs to be equal to t. So if we plug in, yp double prime is 0, and we have plus 2 times the first derivative was a, plus the original function was at plus b. And on the right-hand side, this equals t. All right. So what I'm going to do now is I'm going to just reorder the terms a little bit. Let's move the term with a t to the front here, and then move the terms that don't have a t to the end. So plus 2a plus b, and then the right-hand side stays as t. All right. So at this point, what we want to do is what's called coefficient matching. We want to match the coefficients of like terms. So for example, on both sides, there are terms that have a t. So here's the term with a t on this side. Here's the term that has a t on this side. So their coefficients need to be the same for these two functions on both sides of this equation to be equal. So the t terms need to be the same. So their coefficients need to be equal. So on the left-hand side, that coefficient of t is a. On the right-hand side, the coefficient of t is 1. So a needs to be equal to 1. But we also have constant terms. So the constant term on this side is 2a plus b, and there's no constant term on the other side. But still, those constant terms need to match up for these functions to be equal. So the constant terms also need to be equal, because these functions need to be equal for all values of t. And for two polynomials like this to be equal for all values of t, their coefficients are going to need to be equal. Okay, so the constant term on the left is 2a plus b. And on the right, there's no constant term, so that would be 0. So if we plug in what a is, we know that a is 1. We get 2 times 1 plus b equals 0. And solving for b, we get that b equals -2. All right. So now we know what a is and we know what b is, so we are ready to write down the particular solution that we got. So the particular solution, y sub p, is going to be equal to, so remember the general form was yp equaled at plus b. That was the general form that we had. So plugging in for a, we'll get 1 times t, which is t. Plugging in for the b, we'll get -2. So that is a particular solution to our non-homogeneous equation. So we are now ready to write down the general solution, and this is the last step. So the general solution. So the general solution will have the form y equals yp, so our particular solution, plus yh, the homogeneous solution. So y equals, our particular solution was t minus 2, that's what we just got. The homogeneous solution, we had written that down earlier. It was c1 e to the negative t plus c2 times t e to the negative t. It was the same homogeneous solution for both of our examples. All right, so like I mentioned before, I wanted to start off with some easier examples, but in the next video, we're going to start to up the difficulty with these and take a look at some of the complications that can arise when we use this method.